Morning, folks. I'm going to start working on some problems here as we get going. People might join the chat midway, might stop, do some other things. I'm going to just jump into some problems. I'm recording right now for folks who can't make it today. Right now I'm looking at problem 4. It has to do with atmospheric pressure using an exponential decay function. Now let's take a look at WebAssign here. So their problem says, problem 4, atmospheric pressure. If temperature is constant, then the atmospheric pressure P in pounds per square inch varies with the altitude above sea level H. In accordance with the law, P equals P sub 0 e to the negative kh, where P sub 0 is the atmospheric pressure at sea level and K is a constant. If the atmospheric pressure is 14.7 pounds per square inch at sea level and 13 pounds per square inch at 4,000 feet, find the atmospheric pressure at an altitude of 10,000 square feet. Round your answer to 2 decimal places. So this problem is going to involve us solving for 2 important constants here. First is P sub 0. That's the pressure at sea level. That's actually been given to us in this problem, so that makes it a little bit easier. And then K, right? K is a parameter that's controlling how fast this exponential function decays. That is, K controls how how quickly the atmospheric pressure decreases as we go up in altitude. And we don't know that. We'll have to solve for that given some of the information that we have here. So what I've done on the whiteboard, I've copied down our information here, the sea level atmospheric pressure, the pressure at 4,000 feet, which is 13 pounds per square inch, and then find the atmospheric pressure at an altitude of 10,000 feet. This is of particular interest to me because I actually used to live at 10,000 feet, almost exactly at 10,000 feet in Leadville, Colorado. It's the highest incorporated town in the country. And it was a little tricky to breathe up there, a little rarefied atmosphere. So let me see, I'll switch over, see if I can switch to the document camera now. Whoops. Okay, good. So hopefully everything will remain visible as I work on it here. So I've copied down our equation for pressure. Pressure equals P sub 0 e to the negative kT. And I've also copied down these 2 known pairs of values. So at an altitude of 0 feet, the pressure is 14.7 pounds per square inch. And at an altitude of 4,000 feet, the pressure is 13. So first thing I can do, going into my equation here, I can just insert P sub 0. We know that that's the atmospheric pressure at sea level. I can change that to 14.7 e to the negative kh. And I'll just remind myself that k is a constant, right? That's a parameter in the problem. It's not a variable. It's not going to change. H is a value that might change here. So let's see what we have to do in the problem here. Okay, so they want us to figure out what the atmospheric pressure is going to be at 10,000 feet. Now, in order to do that, we will need to know that growth parameter K. So first thing for us to do is to solve for K using this known pair of values, that at 4,000 feet, the pressure is 13 pounds per square inch. So if I plug in 13 for P, so 13 is my pressure, and plug in 4,000 for H, so negative K times 4,000. Do you see what I have here? I have an equation that only has one unknown in it, and that's that growth parameter K. I can solve for that. I'll do it algebraically on the whiteboard, and I'll need to pause and go use a calculator, type it into the computer to get a decimal approximation. So this process is pretty important. This is something that you'll be asked to do with a variety of exponential functions, that is, solve for an unknown that's up in the variable. That can be challenging. So what we want to do is we want to get the exponential expression by itself first. So that 14.7, I'm going to divide both sides by 14.7. And so on the left-hand side, I have 13 divided by 14.7 equaling e to the negative k times 4,000. I'm just going to write that as negative 4,000 k. Okay, now we're trying to get k by itself. That's our first step. Now is the tricky part. We have negative 4,000 k. It's up here in the exponent. Things can't come in or out of the exponent. Except you might remember one of our properties of logarithms. If we have the natural log of an exponential expression base e, those 2 functions are inverse functions. They'll cancel each other out. So in order to sort of extract that negative 4,000 k, what I'll do is take the natural log of both sides. So natural log of 13 over 14.7 equals natural log of e to the negative 4,000k. Okay, so on the left-hand side, this is some irrational number. We will ask the calculator to approximate it for us at some point, but probably not till the very end of the problem. So still we'll just write that in its exact form, natural log of 13 divided by 14.7. And then on the right-hand side, taking the natural log of a power of e, those will cancel, and we're left with just negative 4,000k, which is good because we know that we can now solve this for k by dividing both sides by 4,000. And so that's our last step in solving for k. So k equals the natural log of 13 divided by 14.7 all over negative 4,000. Okay, so that's our growth parameter k. I'm going to pause the video for a moment and we'll look up what that is as a decimal approximation, and I'll get back to you in just a moment. Okay, I'm back. I've asked my computer to calculate this quantity, natural log of 13 over 14.7 divided by negative 4,000, and that gives us k being about 3.0725 times 10 to the negative fifth power. So a very small quantity there. And hopefully it makes sense why that would be so small. We're talking about by how much the atmospheric pressure changes given a change in altitude of 1 foot. So it's very tiny. K is positive in this equation, but notice that also in the equation itself, we're going to be raising e to the power of negative kh. All right, so what they've asked us to do then is find P of 10,000. So to evaluate P of 10,000, we'll plug that into our pressure equation here. So let's see, P sub 0 is 14.7 times E to the negative 3.0725 times 10 to the negative fifth times our altitude, which is 10,000. And now 10,000, by the way, we could just write that as 10 to the fourth power. We get some nice cancellation here for our expression. So if we want to write this in its exact form, 14.7 times e to the negative 3.0725, I suppose that's rounded at this point anyway, and then multiplying by 10 to the negative fifth and 10 to the fourth, those will cancel to just a factor of 10 to the negative first power. And so again, I'll pause, do that calculation, bring it back, and we'll be done with the problem. Okay, Wolfram Alpha has informed me that this quantity is about 10.811 pounds per square inch. So just to sort of ballpark our results here, at sea level, we have an atmospheric pressure of just under 15 pounds per square inch. At 10,000 feet, 10.8 pounds per square inch. That's about 2/3 the pressure that you'd experience at sea level. I think the really important part here, or the part that's going to be applicable to other problems, is right in here when we were solving for that constant k and we needed to solve for some quantity inside the exponent. We did that by taking the natural log of both sides and then by using the inverse property in this expression right here. Right? If we take the natural log of a power of e, those are inverse functions, and we'll be just left with whatever the exponent is right there. And that's only true if we have exactly the natural log of a power of e. We can't have a number times the power of e. That's why we divided by 14.7 earlier in the problem. Hopefully this is helpful. I'm going to stop the recording here and see if other folks show up for questions.